कृष्णो यत्र पार्थो धनुर्धरा तत्र श्रीर्विजयो भूति ध्रुवा नीतिर्मतिर्मम।
यत्र योगेश्वर कृष्णो यत्र पार्थो धनुर्धरा तत्र श्रीर्विजयो भूति ध्रुवा नीतिर्मतिर्मम। यत्र तनधीं 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 धीं ननन धीरनन तनधीं 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 धीं ननन धीरनन तनधीं 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 धीं ननन धीरनन तनधीं 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 ननन धीं तनधीं ननन धीं तनधीं ननन धीं तनधीरनन धीं ननन धीं धीरनन धीं 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 धीरनन धीं 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 धीरनन धीं
Shri Sai Ram. I offer my humble pranams at Swami's lotus feet. Revered Chancellor Sir, Vice Chancellor Sir, Guest of Honor, members of the Institute Administration, senior professors, teachers, research scholars, students, brothers and sisters. I warmly welcome you all for the second session of today's program, marking the World Space Week, Vistas in Space Science. I now request our guest of honor for this session, Mrs. Nandini Harinath, and Vice Chancellor Sir, to please come on to the stage. I now request Vice Chancellor Sir to welcome our guest of honor with a bouquet. It is my pleasant duty to introduce today's guest of honor, Mrs. Nandini Harinath, Deputy Director of Spacecraft Operations, Indian Space Research Organization, Isro, as we all know it. Madam, a senior scientist who, having worked for over 20 space missions in key designations, is presently responsible for tracking and control of 29 low Earth orbiting satellites and their daily operations. Madam was the director of the RESAT-2B constellation of satellites and the RESOURCESat-2A satellite. She was responsible for the end-to-end operationalization of the satellites. She was also the mission systems lead for the ISRO-NASA collaboration satellite, NISAR, the world's first dual-frequency radar imaging satellite, which will be launched by ISRO in 2023. Along with being and design Deputy Operations Director, Madam is a recipient of various awards, some of them being Astronautical Society of India Space Gold Medal in 2019, the Astronomical Society of India Team Award for the Mars mission, and India Today Women in Science Award 2015. Madam's illustrious achievements have been cited and featured in various movies and books. From being a young girl who was awed by Star Trek to becoming India's proud rocket woman, her journey is an inspiration to millions. She is a living example that women can successfully manage families and achieve miles in their career. Madam will be sharing with us today the glimpses of ISRO's inspiring missions. It is a privilege to have you here, ma'am, with us today. I invite you now to take the stage and enliven us by sharing your thoughts.
Respected Chancellor Sir, Dr. Sanjeevi, Vice Chancellor, Dr. Umamaheswaran, Dr. Seshagiri, and everyone, all the senior teachers here at this institute, and my dear students, a very warm good afternoon. I should say it's an experience for me to be here. It's my privilege, and I hope it'll be a nice experience for you too. Before I actually begin, I just wanted to say, having such lectures and having this Space Week is such a wonderful idea. I must compliment all the organizers and for the management who have thought of this. The reason I was just thinking about it when I was listening to Sir, Dr. Seshagiri's lecture, is pretty simple. Just to quote a small incident from my life, my daughter, she was about 4 years, this is 2 decades back, and normally our working hours, we go in the morning and come in the evening, but whenever we have a launch, for a couple of days or weeks, we'll have to go to office even in the night because these satellites go around the Earth and there can be important operations happening in the night, like because of the geometry basically. So one such incident, I had to go to office in the night time and I was trying to explain it to a 4-year-old that I'm going to office. But you know, she had already grown up and she was 4 and she said, no, every day you go in the morning, but why do you want to go in the night today? And she didn't, unless I explained to her, she wouldn't let me go. Then I said, okay, you know, the satellite, it's there in the space and it goes around the Earth. And you know, night time we get a pass. A pass is the time when you can actually see the satellite. And we want to give some instructions to the satellite and the satellite will send down some data. And then we collect the data and analyze it. And then she heard of that and then she, you know, very concernedly she said, Ma, won't it be very cold on the terrace? Because if you have to talk to the satellite, you have to go on the terrace. So, you know, but then I had to explain the concept of a ground station and the control center, that's where I work. Very relevant today, I took her to the control center, you know, whenever I had an opportunity, I showed her around. And what I'm trying to say is, at this age and the age you are in, exposure to these topics kind of instills that sense of inquiry and curiosity, you know, and when you ask questions and when you think about this, you tend to do great stuff. Believe me, I'm sure there will be Dr. Kalam or Elon Musk somewhere in the audience today. All of you are nurtured and taught so well here, but these talks and listening to such, you know, especially the lecture morning Sir gave, so inspiring. Okay, so with that, let me begin my today's talk. I work in, it's called Isro Telemetry Tracking and Control Center. Till recently, I was in the design team at UR Satellite Center. That's where spacecrafts are made, UR Satellite Center, and I moved from the design team to the operations team here at ISTRAC. So ISTRAC is a place where we track and control satellites. So all the low Earth missions, we have about 27 of them today, as on today. And every time they pass over ground stations, we have about 18 ground stations all over the world. So they track them and get data, and then we like, you know, you have housekeeping here. We also do housekeeping for the satellite, wherein we assess the satellite's health, we make sure it's doing well, and then we command it to do whatever its objective is for. So that is my basic work profile, and I oversee the operations at ISTRAC. So you know, when Vice Chancellor Sir proposed this talk, I was wondering what I should talk to, because you know, Mangalyaan is a very nice topic. You know, even though you speak about it a number of times, even today I cherish every moment of the mission, because it was something I think we just cannot compare that experience with any other launch or satellite. But as you know, most of you would have, you know, heard, read, seen movies about Mangalyaan. I thought I should talk a little more about few other missions that we are doing. And so that you know that it's not just the Mangalyaan, Chandrayaan, ISRO also does a lot of serious stuff. And they are equally challenging. Mangalyaan was out of the experience kind of a mission, but this is, ISRO does many important missions which are very useful to the society, and which all of you would probably using the satellite data and probably in a way involved with satellites even without you knowing it. So that's how applications of satellites have penetrated deep into our lives today. Yeah. So yeah, so I'll just be covering about few things. I think, to have Dr. Seshagiri Rao's lecture as a prelude to mine was a very good thing because he's covered quite a bit of what I wanted to say regarding the application. So we can quickly skip through the first part, which is important applications of satellite data, but whichever I think is few things, there are many, but few things that I think are important and relevant today, I'll just tell you. And, all of us, people who've traveled in Bangalore know the problems with Bangalore traffic. So space is getting cluttered like the way our roads are. In fact, it's much more serious and much more worse. So I just wanted to sensitize all of you on the problem that we are having with space today. We all talk about the usefulness of space, but what we should do to protect the space and how each of us have a role and responsibility towards keeping it clean. I just wanted to emphasize a couple of slides, few minutes on that. Before I talk about, all the missions, I just chose Aditya. A lot is said about Chandrayaan, so Aditya, NISR is one mission which I worked on, so it's, in fact, Dr. Umamaheswaran, before he moved to headquarters, I had interacted with him for a couple of occasions for NISR. He was taking care of the launch vehicle for NISR. And SRE, Dr. Seshagiri Rao is also here. He was a part of our team too when we did this first satellite recovery experiment. It's something that was never covered by newspapers. Nobody outside Isro knew Isro was doing such an important mission. And in fact, it has provided a lot of experience, insight, and information into our future missions like Gaganyan. So I was a key member of that, and that's another mission which I really cherish. We remember, every incident that happened in that mission. So I just thought, because you wouldn't have read about it elsewhere, I thought I'll tell you a little bit about SRE, and then of course, yeah, Mangalyaan, of course, yeah. So let me just skip this because I think we have heard a lot about it in the morning. But then, few things which, sir, extra things that we can mention here is satellites apart from the land and ocean and the air, all that observations that you get from these satellites that we all use. There are two new applications that are coming up. One is called the AIS, Automated Information System of the ship. So what it does is all the ships are supposed to carry this AIS receivers, and these ships emit small signals. And these signals are collected by satellites which are carrying AIS receivers, and that they transmit to the ground. So what happens is it's mandatory for all these ships beyond a particular size to carry AIS. So all the ships carry AIS and keep transmitting the signals. And those signals also contain information about the location of the ship, and that all that information is received by the satellite and further comes to the ground. So a person sitting on the ground knows exactly what the traffic is on the oceans. So this is another new application that is coming up. And similar to the AIS, we're going to have, it's not fully, it's an upcoming technology again. We're going to have similar receivers on the aircraft. So aircraft also will be transmitting in a particular frequency, and all these aircrafts, especially for not only for surveillance but even to know where they are and for air traffic control, this is supposed to be a new futuristic technology wherein all these spacecrafts will be telling each other where they are, and there will be algorithms to determine if some other spacecraft is coming really close. They don't have to get this information from the ATC on the ground. They themselves will be able to assess where they are and who else is there around them. So that is one application. And another application is someone sitting on the ground will have a very clear picture of which aircraft is flying where and what is coming closer to the other. So the entire traffic control can be done very seamlessly using satellites. These are some new things that have come up apart from the routine stuff that you see, which I think we can skip because these are something that all of you very well know. So let me come to another very, very interesting application. The routine applications, I'm sure all of you know by now. All of you have heard of this Navic constellation? Yeah? No? Okay. So then it's a good time for me to tell you about it. All of you have heard about GPS? Yeah, I know. I'm sure nobody goes out, not maybe in your campuses, but just as out of your classrooms without your mobiles. And each one of us, even today when I had to reach here, all the time the navigation is on. So we don't, it's not just about, knowing the way to reach a destination, especially in a place like Bangalore. All of us use it to know which is the route that has the least traffic. So every time, though I go to office for the last 20 years, I'm going the same route, but I still turn on navigation, hoping to reach office in the shortest path. So this is how this has kind of controlled our lives, this navigation and the GPS system. So Isro has its own navigation system. It is a regional navigation system confined to the surroundings around our country. And it's a very indigenous idea, wherein, if you have to have a global navigation, you need to have satellites and coverage all around the Earth. Here, with just 7 satellites kept in geostationary and geosynchronous orbits, we are able to get position and velocity. If you have a receiver, which is receiving Navic data, you will be able to get your position and velocity just like the way you get it with GPS. We're actually using this for many of our satellites and for our launch vehicles. Even the launch vehicle, when it takes off, it needs to know, for many of the algorithms that are used in the launch vehicle, uses the position and velocity, because you need to be on the track. So to determine that, the position, we are using our own Navic satellites. And so with the satellites themselves need to know where they are for many of its autonomous applications. So we are using this, and soon is going to be, I've heard even the ground system, the receivers are being developed so that it's available commercially, and many of the mobile phones probably in future will be using this. So this is one of the very nice applications that we have. And then if you're using it in an aircraft, obviously these signals are corrupted. Like, even when you use the GPS, it'll say you turn, but when you don't find a turn there. And sometimes when you reach a turn, you're not sure whether to turn here, to turn there. That is because the position accuracy is a bit poor. It is of the order of 10 meters. So when you reach a junction, you're not really sure, is it this or the next? I mean, I'm sure all of you faced this situation with the GPS. So, but it can't happen. It's okay on the road, you can go take the wrong turn and then come back, take a U-turn. But can't happen with the aircraft, wherein things are very critical. But you need to know the position very accurately. So for that, there are so many errors that accumulate in the signals that we receive. It could be because of the atmosphere, it could be because the clocks are uncertain, the clocks may be having a bias. All these corrections are quickly done on the ground. The data is received by multiple stations all around, and corrections are done and uplinked to an aircraft very precisely. So this system is called Gagan. Yeah, another very, very interesting application is the search and rescue. So a lot of people, just having a GPS is not sufficient. Suppose I'm going on a mountain somewhere and I have a GPS and tells me where I am, but I'm actually lost because I don't know how to reach the next point. So, and then I'm also in distress. So I need to communicate to a person saying that, okay, I'm in distress, I'm lost, I know where I am, but how do I communicate to a team which is on the base, or if it's an aircraft, if it's crash landed. So there's a consortium of organizations that came together, and they said, let's have a search and rescue distress system, wherein a beacon emits signals in the UHF and VHF that reaches the satellites, and so these signals are not going every time. So whenever there's an SOS or I'm in distress, I press the distress signal, and the signal reaches the satellite, and from the satellite it reaches the control center, wherein it gets processed, and then there's a ground segment, whole lot of ground segment interfaces to communicate this to the rescue team, and people are rescued. So we have one such search and rescue mission control center in our own office in ISTRAC. So this is another very important application of the satellite. Yeah, this of course all of you know how we use satellite data for disaster management. Yeah, now let me come to the next topic, topic number 2. Someone can actually tell me about the time because, yeah, so we started at 1:20, right? Yeah, okay, okay. So, like I said, space is cluttered, cluttered, cluttered. Now, why is it cluttered? People have been using this quite irresponsibly, I must say. There have been organizations who just, the spacecrafts have been exploded and intentionally or unintentionally, all this debris has been left behind. All the launch vehicles that we launch to use, to put our satellites in space, all the spent stages of all these rockets are there. There are debris from, like say, from ISS. People have started living now in space. You know, there's recently a lecture I attended by Blue Origin, wherein they said that they want to do business from space. They said you know, if you want to go on a holiday, maybe 1 decade later, and may not even be that far, you can actually, you know, instead of booking a resort somewhere here, I could actually go to space and have a holiday. Or if we are having a lecture like this, I need not be speaking to you from the auditorium. Maybe I'm speaking from space. You could have seminars, conferences, businesses, holidays, everything from space. So this is what people are up to these days. But then it has, there are issues with all this. And even the SpaceX satellites, which sir was mentioning, Starlink's satellites, there are going to be 42,000 of them. So you can imagine, you know, astronomers are already complaining, and of course, but then there has to be some regulation, and everybody wants to use space for the best of their technology available, but then how do we regulate them? So this is how you see how the space debris actually grew from 1957 to 2015, and this is how it looks. I don't know, maybe if you can dim the light, you can see there are like hosts and hosts of particles all around. So now, like I said, why are we having so many, so much of debris? It's because there have been actually instances reported of collisions in space, collision between live satellites and live satellite and a debris. These have been reported. And then there was an entire constellation which actually, which didn't work and which is left, which broke up and which is left as debris to go around the Earth. So these are some of the things, you know, this is again something that we found, someone actually found a Delta II rocket in Oklahoma. And you can see the space shuttle, all of you have heard about the space shuttle, how the window was damaged by a debris. And here you can see the Hubble, the famous Hubble telescope that we have in space. You know, the panels there also were hit by small debris and captured by cameras. So what are we doing about it? So just to give you a small brief on what everybody, so obviously now everyone is concerned because it's not just that debris is going to follow one country's satellite or one organization, it can hit anybody. So then everyone has come together now, and then you have this organization called IADC. So they are taking some measures now. They're saying that every satellite that goes up should plan for a decommissioning and a re-entry. So we should carry enough fuel, not just to go to space, but also we should have enough fuel to come down. And there is a limitation. Okay, if it should come down within say 5 years or 20 years from the time it stops functioning. So these are some things that they said. And then they said, what else can we do? There are now so many new technologies coming up. Maybe one of you can come up. This is one of the very, very challenging field today. How do you clean up space? So you can come up with your own ideas. There are people who say that, you know, they've found big clamps kind of thing which will grab this debris and bring it down. There are so many ideas. They look very, very imaginative today, but I'm sure they'll all be realistic tomorrow. So yeah, this is one prospective area for all of you to think and work on. Yeah, and there is many spacecrafts, if they don't have fuel, but there are ways to create, larger surface area so that it decays faster. So this is another method to bring down the satellite quickly. Yeah, so now we'll come to the last part of the lecture, that is, I'll talk a little bit about SRE, Aditya, and Mangalyaan. So this was a mission way back in 2007. So Isro decided that it will send a satellite into space. We call it as a vehicle because it's going to come back also. Actually a capsule, space capsule re-entry experiment it was called. The challenging part was never had a satellite which had gone up had come back and we had recovered it. It was the first time in a full form, in an integrated, full structurally integrated form to recover a satellite, and it had to work till it touched down. So this was the aim and objective of the satellite. It is a kind of prelude to our Gaganyan and future missions wherein we want to send humans and then bring them back safely. But this was not today, but way back. Probably, yeah, 2007 was re-entry. But why was it so challenging? So it's, we had done enough number of satellites to go and orbit and send us data, collect data, but there was never an opportunity for us to bring it down. So here there was a plan wherein the satellite itself had this retro rockets, or we call them thrusters, wherein you decelerate the satellite. You heard in the morning about how they move when they are in the orbit. You heard the principle and the equations and the velocity it has when it's in orbit. But if it has to re-enter and you have to maintain the integrity of the satellite, then you had to actually brake, or you have to decelerate the satellite sufficiently. So then there was a deceleration burn to redirect the trajectory from the circular orbit towards the atmosphere or towards the impact point. And the good thing about re-entry in Earth, unlike re-entry on a moon, is that we have a natural atmosphere which decelerates or decelerates the satellite on its own. You don't have to do anything extra. The atmosphere itself is a good layer, and when the satellite touches the atmosphere, it will decelerate. So that doesn't happen on moon, and the atmosphere is very thin on Mars. So here we have an advantage. But with the advantage, like, everything that has a positive has a negative. With the advantage is a very big problem. So as the atmosphere, as there is a velocity reduction, it generates enormous amount of heat around the satellite. So the satellite had to be thermally protected against the re-entry heat. And more importantly, the nose had to be specifically designed, because the nose is going to bear the brunt of the re-entry. So the design for the thermal protection system, and then managing the thermal control, and then it has to further decelerate. So the atmosphere removed most part of the energy, but then it still cannot fall with the same velocity. It had to be further decelerated. So then there were parachutes which would deploy, and then there's a flotation system, and with which the satellite would fall in the ocean. So this was the plan. So, so all this design was new. So our team, the URSA team, in coordination with the VSSC team, because the entire, from the re-entry to the touchdown, it was a collaborative effort between various organizations. In fact, SHAR also, because the recovery was happening close to SHAR. So I'll tell you one incident that happened. So everything was planned perfect, to the T. Then the most important was this burn wherein the spacecraft reduces its velocity. So that also happened very well. And there also it used the GPS to navigate and reach the exact, we call it as a pillbox. So at the atmosphere entry, there's a pillbox. If the satellite reaches the pillbox, then you know for sure it's going to impact at the point where you want it to. So that was here. You can see this was about 140 kilometers from SHAR, and then this was the impact point, and there were ships and helicopters waiting all around the impact point in order to track the satellite. So even though it was the first time for Isro, this re-entry happened successfully, and the module was recovered. So this is... No, there's a small story. I'll just take 2 minutes to say, even though everything looked good, but then we did have our tense moments. So when I said that we have this atmospheric re-entry, because of the ionization that happens during the re-entry, for 2 minutes we have a blackout zone, wherein we don't get any communication from the satellite. I'm sure all of you have seen Apollo 13 and then the famous dialogue, "No, Houston, I'm in trouble, I have a problem." So that's a natural thing that has to happen to any vehicle that is entering the atmosphere. So we were praying, and because those 2 minutes you don't get data, and then it's like you don't know whether, and that's the time wherein you want to be sure whether the satellite is intact or not. But if it did disintegrate, you obviously are not going to get data after that. So then those 2 critical minutes, everybody at the control center was praying and hoping that everything would go fine. And even though it was the first time, we did get data after the 2 minutes. Then there was another critical point wherein the satellite, as it comes down, morning he explained the concept of AOS, LOS. So even though you're at a ground station, because of the curvature of the Earth, at the impact point, you don't get data for some time, because the satellite has gone beyond the curvature of the Earth and beyond the visibility of your station. But then you had a helicopter and ships all around. But then we see the spacecraft had survived the re-entry, and then it had beautifully come down, and everything seemed, and all of this was automated. There was no intervention from the ground. So even though it was the first time, everything worked beautifully, every software worked, and suddenly the telemetry data vanished. And nobody had a clue of what happened, where the capsule went. So it was a tense moment at the control center, and all of us wondering what had happened. Then it was almost an hour, and the rescue teams from SHAR went everywhere looking for the capsule, and they did not find it. And then we said, we did everything, 99% seemed okay, but 1%, where did the capsule go? How come we are not able to locate it? And what happened? Why did we lose telemetry? And then we found out, one smart person in our team decided we had 6 samples of GPS telemetry after the re-entry. So we had 6 samples of the position and velocity of the capsule after it had re-entered. So that person went back, and we wrote a program on the fly to extend that 6 points to the ocean, and then we knew where the impact was. So that was immediately conveyed to the team at SHAR. We had a rescue team, and you won't believe it, it was exactly at that point. It was exactly at that point, and these were the pictures that you see when people took. People actually, I heard in SHAR, prostrated when they brought the satellite back, because the first time an object from space had come. So yeah, that's what I'm trying to say is, these are challenging, these type of missions are challenging missions, and irrespective of how much you plan, there's always something unknown that's going to happen, and you need to be prepared for that. Yeah. That's the same story about life too. Just to extend the corollary to our day-to-day life, whatever we do, there is always something unexpected that's going to happen. So we need not be worried about it. Yeah. So the pictures are not very clear, but I wanted to tell you a little bit about NISAR, because it's an upcoming mission. All of you are going to read about it in the papers very soon, and you must have been reading it. This is the first time ISRO and NASA are working so closely together. So we talked of nanosatellites, isn't it, in the morning? So this is a huge satellite. So this antenna that you see is going to be 12 meters. 12 meters is something probably a little bigger than this stage. So, and the boom is 9 meters. And it's going to carry radars, L-band radar and an S-band radar. L-band is given by NASA and S-band is given by ISRO. And this is going to measure everything about the Earth's ecosystem. How the ice glaciers are melting, how the ocean water level is raising, and it's also going to measure your plate tectonic movements. It has a capability to measure 4 millimeter change in the Earth's tectonic plate. To that accuracy, it's going to work. So this is something that all of us are looking forward to, and is going to be launched sometime next year or late next year. And this data is going to be available freely for everyone. The good part is this is declared as a science mission. So this data is going to be available free of cost for everyone around the world. And as on today, It's probably the most expensive satellite ever made. And yeah, so this is about NISAT. Yeah, and all of you heard about L2 point, wherein the James Webb telescope is sitting at L2. Our own mission is going to sit at L1, the Lagrangian point. And I like the way sir put it. Trishanku, you said, sir? Yeah, I like that word. So this is going to sit at L1, and it's going to get us data about everything about the sun. A lot of people think that it's going close to the sun. No, it's not going close to the sun, but it's going to be sitting at L1, which is a very stable point from where you can observe the sun constantly all the time. And every dynamic activity that is happening on the sun, it's going to capture it and then relay the data to us. So that's about Aditya. Yeah, so what is the future? Like I said, it's not just about conducting business or having seminars and conferences in space. People are also thinking of habitating the space, and I don't think we should be left behind in any way. So soon, I'm sure all of you heard the statement from Carl Sagan, who said, if survival is long-term survival is at stake, if you have to guarantee the survival of mankind and mankind surviving forever, you need to habitat other planets too. So very soon, I think the resources, the way we are using up our day-to-day resources, this might happen a couple of decades from now. So there is going to be a race on reaching to the other planets. Whoever reaches there first is going to claim their piece of land and say, this is mine. So I don't think we should be left behind in that. But I'm not sure if that was the motive. The motive was to prove that we have the technology to reach Mars. We have the capability to go beyond the gravitational pull of the Earth. And so it was more to demonstrate the capability of leaving the Earth's gravitational field, getting captured around Mars, and orbiting a planet. So that was the basic incentive for our mission. Yeah, of course, there are a lot of similarities between Mars and Earth. Mars is inclined to the ecliptic the same way the Earth is. You all know about the 23 degrees declination effect that you have, and because of that you have the seasons. Mars also has very similar inclination. So because of that, the seasonal effects are the same. But because it's a farther planet from the sun, it has some few other issues. Like it is, in terms of its constituency of the atmosphere, is extremely different. And a year in Mars is 1.88 years around the Earth. But then though we say, in terms of geometry, there are a lot of similarities, but the way it is composed, it's extremely different. And what people feel is, the scientists feel is, if you know or if you study the composition of the atmosphere or the geology of Mars, you will probably know a lot about Earth itself, because Mars has preserved the history. Earth has had so many things happening on the surface, right? I have volcanoes and eruptions and so many things happening on the Earth. Earth probably, even if you study the geology, you will not know what had happened or how it was formed. But people say when you study Mars, you might get a lot of clue on how the Earth was formed or even how the solar system was formed. And then there is one curious question all of us ask. Like morning he showed so many galaxies and such a big universe or a multi-universe. Are we alone in this world? Or is there someone else discussing these topics the way we are discussing this today? That's a $1 million question that all of us have in our mind, to which we don't have answers today. So how did this Project MOM begin? So there was, I'll just explain to you in 2 slides on why there was such a race and a run. Like you could have done it leisurely, right? Why did you want to do it in 18 months? And what was the challenging thing about it. The challenging thing is from the time, being a government organization, you do have to get approval from the government to do a mission like this. You need to get sanctions. So from the time we got a sanction to the time we had this launch window. Why is the launch window important for interplanetary? Because I think most of you are science students, right? So I'm sure the very basic science that you will understand why there is a launch window constraint. And then it was our first interplanetary mission. It had plenty of challenges, not just in mission planning and executing navigation, but it also involved a lot of developing new hardware. Deep space communication is something that we hadn't done before at all. So the receivers that we flew had to receive the signal from 400 million kilometers. So you can imagine all the noise that is there. Amongst all the noise, it had to pick up that signal to understand what it was supposed to do. So there was a challenge in the hardware development also. Apart from that, the most important thing was how to reach. How do you can always study a lot of theory textbooks and do a navigation, a trajectory. You can draw the trajectory. I mean, that's also challenging, but you can still do a trajectory today on paper. But once you are there, how do you know you are there? How do you know I'm on the right trajectory? So that was the bigger challenge here. So these were some of the important challenges that we had. Mission design, integrating the satellite and testing it in all those 18 months. I still remember when we were asked to work for the Mars mission for the first time, none of us had a background on interplanetary missions. So we started with basic textbooks and sitting in the evening together discussing what had happened, who are all the people who went to Mars, why had those missions failed, and we had to learn from scratch when we came across this, when we were asked to do this project. Obviously now we have a certain level of experience and expertise, but it was a different story at that point of time. And then everybody says this, and I think it's true even in real life also. One need not always do the mistakes to learn. We always should learn from other people's mistakes. And so, so we kind of went and poured into the literature and found why did 40% of the missions that had flown earlier had failed. And we had analyzed each and every failure so critically, and obviously you don't want to do the same mistake again. So learning from other lessons from others' mistakes was one of the key things in the mission planning and developing the hardware and management. And then like I said, in the case of SRE, always, citing solutions on the fly is the most important thing, I think, for any space mission. So, because not everything, you must be reading of so many incidents happening to even the most professional space organization or the commercial organizations. Always something that unexpected can happen. To cite solutions on the fly and then to find solutions on the fly is something that we at Isro are all very good at, and we are all proud of it. Yeah. So this is, I mean, for the science students up there, basically the spacecraft had to leave something called the sphere of influence. So as long as an object is around in the sphere of influence, it will be going round the Earth, and it will never be able to leave the Earth's atmosphere. But once you have that little escape velocity, I'm sure all of you have read escape velocity. So once you get that little escape velocity, you will be going out of the Earth's sphere of influence, and you will be going in a cruise or in a trajectory around the sun till you reach the Mars. There you will have to do a retro burn again because of the velocities. Morning sir explained the velocity is so high. If you continue, you will probably just be a flyby. You will go reach Mars, but you will just fly by but there at that point you need to decelerate and again get into the Martian atmosphere. So it was a complex 4-body problem, and the entire trajectory was divided into 3 parts. We call it as a patched conic problem. So basically, all of you know it's very easy to solve a 2-body problem, but when you get a 3-body and 4-body, it gets more complex. So this entire complex trajectory was broken up into 3 2-body problem. So this is, I think so this is what I was trying to say. So, so when the satellite is around the Earth, it is between the satellite and the Earth. They are the two bodies. So once it gets this escape velocity and goes into a trajectory towards Mars, it is like satellite and the sun. It's a two-body problem. And then when it's around Mars, it's Mars and the satellites. Again, it's a two-body problem. So this three conics were, it's a patch conic problem. So these three parts were separately attacked and then stitched together. So yeah, for those people interested, I thought I should bring a little bit of numbers and in this presentation for those who are interested in science. This is very simple. This, even a high school student would understand why we had this launch window of 18 months. So basically, if you look at this, the distance between the sun and Earth is 1 AU. Again, morning sir explained, so I'm happy actually, sir. A lot of things that I wanted to say, you said. So it saved my time. So this distance between the sun and Earth is 1 AU, but distance between the sun and Mars is 1.5 AU. So if you have to draw, so this is the orbit of the Earth around the sun, this is the orbit of the Mars around the sun. But if a satellite has to go from Earth to Mars, it has to follow this trajectory. But you know by simpler Kepler's law that for every ellipse you have a semi-major axis. So if this is 1 and this is 1.5, the semi-major axis of this trajectory would be 1.25. It's very, very simple mathematics. So, but then if the ellipse has to have 1.25 as a semi-major axis, the time taken for the satellite to reach from here to here would be about 0.7 years. So it's again a rendezvous problem. I have a satellite that can follow this trajectory, but what use? If the Mars is not there at this point, when the satellite reaches, there's no point following the trajectory, right? It's a rendezvous problem, and a rendezvous problem that has to be accurate to the order of seconds. So when Mars is exactly at this point, the satellite has to travel this entire path and be there. So you're trying to target a 50-kilometer pillbox from somewhere like a distance of 225 million kilometers. So now for this to happen, now I said this trajectory takes about 0.7 years. Now in 0.7, but you know that the Mars takes about 1.88 years. So in 0.7 years, Mars moves only 134 degree, but this is actually 180. So what you do, if the Mars is ahead by 180 minus 134, that is 46 degrees. So if the Mars is ahead by 46 degree, when the satellite leaves the Earth, then there can be a rendezvous. You got it? So why Mars should be ahead by 46 degree to have a rendezvous? Now this 46 degree geometry happens once in 18 months. That is what is dictating the launch window, or that is what is dictating our constraint. That's the main constraint for the launch window. Okay. So this is what I was trying to say. So this is the orbit around the Earth, and then this is the 225 million kilometer. And the challenge here was every time you are on this trajectory, there are so many perturbative forces acting. It's not just the spacecraft itself, even something like sunlight, or we call as solar radiation pressure, that also can disturb the satellite's track. So when the solar radiation pressure acts, it gives a torque, and that can also disturb the satellite. Then we have something called reaction wheels. Occasionally, they have to be desaturated. So then, the spacecraft fires small thrusters to desaturate the wheels. So now all these are causing disturbances in the trajectory. Though when I left, I thought I'm on the right path, but all along in the 9 months, I need to do course corrections because there are so many other disturbances acting. Now, all these computations were done. The challenge was to not just predict these disturbances and minimize them, but the challenge was also to know the position very accurately. So we employed different methods, the usual methods of ranging and Doppler. I don't know how many of you have been caught by traffic police for speeding, right? Traffic police also uses this Doppler system for to know how fast you're going. So we use something similar. Conceptually, it's similar. You use the Doppler to know where you are. So apart from the Doppler and range, we had to employ some very highly technical and complicated, or let's say sophisticated methods to determine the spacecraft's object. This was called delta DOR. Yeah, so I won't go into the details of that, but then what are the other challenges? So this is one type of challenge. What are the other challenges? See, suppose, I'm talking to you and the sound waves are reaching you in no time and you're all able to hear me, and I can actually see from your expressions, and whenever I'm asking a question, people are responding and nodding your heads. I can see that. But what if the conversation was like that? I'm talking to you and you hear me after 20 minutes. And then you say yes or no, and I hear that after another 20 minutes. So you can imagine what kind of a seminar we can have. So this is the problem with trajectory to interplanetary missions. So you send a signal from here, you want the satellite to do something, it will reach after 20 minutes, and then the satellite does that activity, and then you get the confirmation of after another 20 minutes. So this way, to micromanage is what the term we all mission planners use. It was impossible to micromanage the satellite because of the light time delay. The delay comes only because of distance. The speed of light to travel this distance of 225 or 400 million kilometers takes 20 minutes, 8 minutes to 20 minutes. So that was the kind of delay we were dealing with. Now, what does the satellite have to do? Because it has, we have this problem. So the satellite had to be built with a lot of autonomy. Okay, even though I have controllers sitting on the Earth, I should be able to take care of myself. So we built in a lot of intelligence for the first time in the satellite, so that even if something went wrong, even before somebody sitting on the Earth came to know, the satellite would do some minimal configuration changes to make itself all right. So this was lot of hardware and software involved. So this was also developed for the first time in the Mars mission. And then it's not just the light time delay. There are also other more interesting things happening. So all these objects are dynamic. The Earth is moving, the Sun is moving, as he said, and Mars is moving, and the satellite is moving. Now, you can reach a geometry wherein the Sun comes in the middle, and you have the Earth on one side and the satellite on the other side. The Sun is actually physically obstructing or coming in between the two. So you actually cannot command to the satellite even if you wish to. So for about 15, we call it as a blackout zone. So for about 15 days or so, you are not able to communicate to the satellite. So even in those times, the satellite needs to be totally on its own. It needs to take care of itself. So this is another reason why we had built the autonomy. Yeah, this is just to show you the blackout. And there's something called whiteout. It's not just the Sun coming in between. Even if Sun is behind the ground station, it can still cause problem because for the signal to reach the satellite. So this we call as a whiteout geometry. So these were the, yeah. So this was a basic requirement or the fundamental reasons why we had built autonomy in the system. So now coming to the other, the unexpected events, it's always good to know, even though we had done lots and lots of studies and then we had done a zillion simulation, something very unexpected happened. So this was sometime September 24th, we were around the Martian orbit. Within a month, we heard that there was a comet. Comet was coming from Oort cloud. The comet was coming from outside the solar system. And that was approaching very close to the satellite. So there were two problems with it. We just reconciled and we said we were happy, we are there in the Martian orbit and everything was going on smooth, and then we know that this comet is coming. It's once in a probably million, zillion year opportunity, for us, for a comet from not even in the outside the solar system to come there. So, but there are again two problems. One is, we were ambitious enough and we had a color camera in the Mars mission. So we wanted to take a picture of the comet. So we were ambitious about that. But we were also a little worried because all of you know these comets have a shower. They leave behind a trail of dust particles. And we didn't want to get hit by any of those dust particles. So quickly, again, the team sat and then we worked out a strategy so that as soon as the comet approached the Mars as a planet, we would would be on the other side. We would be 180-degree diametrically opposite. We kind of hid behind Mars, and just as the comet passed, we would emerge out and take a picture from the backside. So this is a picture of the comet shower that we took from our own camera, Mars color camera. Yeah, there are a lot of achievements. I'm sure all of you know. We were the 4th space agency and the 1st Asian country to reach Mars, and the mission itself won number of awards. It was recognized by all over the world because the first time any country had succeeded in the very first attempt. And the mission objectives were met. It was planned for 6 months, but then it went for a really long time. Yeah, this was I always like this picture because this was a full disk image. You know, if someone had to take the entire Mars disk in one camera, no other satellite actually has done this because their orbits are closer to the Mars surface. So if they have to make a full disk image, they have to take number of pictures and mosaic them to make one picture. But our, you know, even though our orbit was at one end we were close and one end we were far, we kind of utilized that opportunity that we were far off, and we were able to get this entire Mars disk in one frame. So this image was also widely appreciated because this hadn't been done by any other mission before. Yeah, this is a Mars color camera. Yeah, and this was another challenge that we had. You know, Isro also has a lot of design reviews going on when we have any mission. Our strength is in our review system. So even though I'm a designer and I plan a lot of things, I need to convince the review board that I'm right. And the review board takes hours and days. They can sit on a problem and grill you to the end. So there was a lot of discussion in the review board that after we get capture on the Mars, what do we do? So then there was a proposal that since, you know, the proof of the pudding is in eating, right? You've reached Mars and you tell everybody we reached Mars, they will say, okay, fine. But if you take a picture and then show them, yeah, we've reached Mars and this is the picture I took. So that will have a totally different impact. So this was, but then it also, there was a worry that, you know, so we really don't know the environment and we've just done a maneuver to deboost and then we haven't fully understood the orbit geometry around Mars. Do we take a chance to operate our payloads at that point of time? But then we said, no, we should do it. And then there were enough simulations. I mean, everything it's not just the spirit and the idea, but enough simulation and groundwork was done to ensure that it was a safe operation. So just after 40 minutes after the Mars insertion, the camera was operated and we took pictures. And even while the Prime Minister was speaking, the pictures were getting downloaded at the background. And within an hour or so, they were released. So yeah, this is one of the first pictures that came from the mission. Yeah, Mars is also home to, you know, this highest volcanoes. The highest volcano is in Mars. The second highest also in the entire solar system is also on Mars. So we had opportunity to look at all these volcanoes. By the way, Olympus Mons is the highest volcano in our solar system. Yeah, these are some of the pictures of the crater. May not be very clear on the screen. Yeah, so I must say that apart from the color camera, we did have other instruments, a methane sensor, a thermal infrared sensor, and there was an atmospheric analyzer, which we called as MENCA, to know the constituents of the atmosphere. Obviously, those are very scientific, and those results cannot be seen in terms of pictures. But what we've heard from the scientists is there are a good number of publications, and whatever payload it carried, it did give us good results and a lot of insight to the scientific community on the composition of the atmosphere and other geology factors. Yeah, thank you.
Thank you so much, ma'am, for your extremely inspiring and informative talk. Thank you for explaining to us in very simple words the applications of satellites and space science in multiple areas. You have enlightened the young Indians and future scientists here of the responsibility of the world to space and the need and means for space debris mitigation. Your first-hand account of the Mars mission was so heartening, and I'm sure many of us here are encouraged to dream big. As you said in the beginning, interactions with great minds like our guests for the day will surely kindle the curiosity and interest of all of us in space science and the missions of Isro. Thank you so much, ma'am. Once again, let us give a big round of applause for madam. I now request our revered Chancellor, sir, to please grace the dais. I would now like to request Chancellor Sir and Vice Chancellor Sir to honor our guest speaker, Mrs. Nandini Harinath, and gift her with a token of our love and gratitude.
Om Shri Sai Ram. I offer my sincere prayers to Swami. I welcome you all to the second session of this afternoon. Respected guest speaker of the second session in this fine afternoon, Dr. R. Umamaheswaran, Chancellor of the Sri Sathya Sai Institute of Higher Learning, Sri Chakravarti Garu, Vice Chancellor of the Sri Sathya Sai Institute of Higher Learning, Dr. Karini Sanjeevi, Registrar, Directors, distinguished faculty members, esteemed elders, and my dear sisters and brothers, a loving Sai Ram and a very good afternoon to all of you. I now request the guest speaker, Dr. R. Umamaheswaran, and the Vice Chancellor to come and take their seats on the stage. I have the pleasant duty of introducing the final speaker of this afternoon, Dr. R. Umamaheswaran. Dr. Umamaheswaran completed his BTech in ECE from the College of Engineering, Trivandrum, and Masters in Software System from BITS Pilani, and pursued his PhD in Electronics and Communication from NIT Trichy. He is a domain expert in the field of launch vehicle system electrical integration, checkout, ground station, avionics, system engineering, as well as space policy planning. Dr. Umamaheswaran has been with the Indian Space Research Organization, ISRO, for over 35 years. He has worked in the Vikram Sarabhai Space Center of ISRO for 31 years in various capacities, including the project director of GSLV from July 2014 and deputy director of VSSC in the avionics division from May 2017. He was assigned to serve as the Associate Scientific Secretary at ISRO headquarters, Bangalore, from May to August 2018. And later, he served as a Scientific Secretary. He assumed charge as a Director of the Human Space Flight Center, HSFC, Bangalore, in 2022. Apart from his immense contributions to ISRO's international cooperation by serving as the co-chair of joint working groups with many space agencies, he also signed the Joint Declaration of Interest for Space Climate Observatory, SCO, at Paris in June 2019 on behalf of ISRO. He represented India in the UN Committee of Peaceful Utilization of Space meeting in June 2019 and led the ISRO delegation in Asia Pacific Region Space Agency Forum, APRSAF 2020. He was elected as the chair of Working Group on Long-Term Sustainability of Space Activities in the UN Committee of Peaceful Utilization of Space Scientific and Technical Subcommittee. As LTS chair, he is working with the UN member countries for bringing out international guidelines for the long-term sustainability of outer space activities. Dr. Umamaheswaran is also currently member of Board of Trustees of the International Academy of Astronautics, member of InSpace Board, fellow of Aeronautical Society of India, Astronautical Society of India, and several other international and national bodies of engineering and science. Dr. Umamaheswaran has won several awards, including ISRO Individual Merit Award 2013 and ISRO Outstanding Achievement Award 2018. He also received the ASI ISRO Award for the year 2016, the Dr. Biren Roy Space Science and Design Award from Aeronautical Society of India 2019. Today, Dr. Umamaheswaran will be speaking to us on the topic Indian Space Odyssey, Sounding Rockets till Gaganyan. I now invite Dr. Umamaheswaran to come and address the gathering. Dr. Umamaheswaran.
Hello. Hello, am I audible? Yeah, right. Thank you. My pranams to Bhagavan. Most respected Chancellor, Sri Chakravarti. Vice Chancellor, Dr. Sri Sanjeevi. My dear colleagues, my Guru, and Madam, and all the other senior colleagues who are assembled here, as well as the stars of today and the future of, or rather I would say the next gen in whom we have a lot of faith. A very, very good afternoon. This is the time for sleeping. I know all of you after lunch would be in a mood to sleep, so I hope my talk will not further induce you to a faster procedure of sleeping. So let me also thank the Vice Chancellor for giving me this opportunity to come to this very holy place and stand before you and share some of my thoughts with all of you. First of all, I think I should thank Bhagavan, because lots of instances were there where I have heard of Bhagavan and through my relatives and my friends, and many times I have thought I should one day I should come here, but it never happened. Probably Bhagavan thinks, why the hell you didn't come here earlier? So I will make you to come here. Maybe I never dreamt that at this point of time I will be reaching here, so maybe he has led me here. So once again, thanks to him. Today morning I had a wonderful experience, a very great ambience, an ambience of only goodness all around. That's a very rare sight to see, and I thought I got a lot of energy by sitting during that yajna and the chanting that was happening. So it's really wonderful. I really got I would say a great and wonderful experience. So I'm enthused, more enthused to talk to you now. So basically I'm not going to talk anything too technical or anything like that. More or less I am trying to tell you a story of how Isro, the genesis of Isro rather, how it has expanded its horizons and where are we now when we are talking about a very complex and challenging program like Gaganyan, mission to space, manned mission to space. So that is what I am, that's what I think I should do. So I will narrate the story of Isro. So it's also a story of my evolution also, my career in Isro also. 1963 was a very, very unique year in the world scenario due to many, many events that happened. It was the year when the first woman went to space, Valentina Tereshkova, in the Vostok 6 by Russia. In a lighter vein, a very unique event happened in Buckinghamshire in England, the Great Train Robbery. Many of you have heard. It happened at that time. A historical speech, I would say, which still resonates if you hear in YouTube. I Have a Dream by Martin Luther King. That happened in 1963. And it was also the year when Isro was born. So that is the beauty and that is the importance of 1963. And in a very lighter vein, it was also the year when I was born. So my history is entwined irrevocably with the odyssey that Isro has come up to this stage. And maybe that is fate. So the first sounding rocket, we started very humbly by sending a Nike Apache sounding rocket from Tumba on the southernmost part of our state, Kerala, in the city of Trivandrum. That happened in November 21, 1963. And incidentally, the next day, John F. Kennedy was assassinated. So the story began much before that, when a great visionary like our we call him the father of Indian space program, Dr. Vikram Sarabhai. He envisioned the entire gamut of how India should enter into this space exploration, space technology, and he was very, very clear in his vision. He repeatedly told, and I am very proud to repeat this, he was always telling that we should be second to none. Is it on? Is it okay? We should be second to none in the committee of nations to utilize the technology from space and the data from space for the benefit of our own persons and our own society. So these are his words. We must be second to none in the application of advanced technologies to the real problems of man and society. This is exactly what ISRO has been doing for the past 60 years. Precisely, this is the goal. Whatever we do, whatever experiments that we do, whatever missions that we take up, ultimate goal has to be this, and ultimate goal will be this. And definitely this is a mix of many aspects which I will talk to in the coming slides. And also, you may ask then why you are going ahead with space missions. Definitely that is also for the addressing our problems to the society only, and also it is also our duty to see that the scientific temper is always kindled in the next gen. That is also extremely important. We should always trouble or attack the curiosity of the next gen. Then only different thought processes will come, and from then only new ideas will emerge, and from that only new technologies and new missions will emerge, which will benefit us. So this is exactly what ISRO is doing and will continue to do. So I would say that 1960s, when the first Nike Apache launch was executed successfully, there also I would like to tell you that ISRO is an organization which is always looking for collaborations. From the beginning, industries were part of us. We never thought industries as our vendors or something like that. From the beginning, industries were our partners, and whatever technology we had given to the industry so that they can make themselves, and that will benefit them as well as the society as well as ISRO. This has been the attitude that we have been taking, and we were not shunning the international collaboration also. Definitely we were, let me say, 40 years behind as far as the achievement in spaces are concerned when we started in 1963. So definitely we need international collaborations also. And the first mission, Nike Apache mission, the rocket was from NASA, while the payload was from ESA. So that is so from the beginning, international collaboration also, we were very strong, and still, even now, our collaboration with NASA, ESA is extremely strong. So that is what I would like to stress here. And during the 1963 onwards, it was a kind of quest, what we should do, what are all the technologies that we should earn, we should understand. Everybody was starting from scratch. And Sarabhai was a leader who always initiated competition among many teams. He would propose a problem and ask 3 different teams to do the same thing. And the 3 different teams will compete among themselves so that ultimately you get the best product. So this has been the kind of culture that was built in. I will come to that culture later, because that's also very important, and it's something which is inbuilt into the characteristics of what an organization called ISRO is, which I would like to convey to all you people. So basically, 60s were, I would say, a period of quest. When it came to 1970s, the kind of expansion that we are in now started. So basically, I would say the first spaceport, the only spaceport we have now, Sriharikota, it was operationalized in the 70s. The basically earlier everything was concentrated in Trivandrum, in the Tumba, the Thurls, and including the basic designs of satellites were carried out there. In the 70s, it was decided that we need a separate establishment to design and development the satellites. So it was brought to Bangalore, and the first satellite center was established there. Even the establishment of Isro, Isro was established in 1969. In 63, the organization was called INCOSPAR, Indian Committee for Space Research. It was started in that manner under the Department of Atomic Energy. So that was the beginning. And let me also tell you an interesting anecdote or a story of the beginning of ISRO. As I said, the Nike Apache rocket was sent from Tumba. The land in Tumba was acquired by the government of India in a very interesting manner. Actually, that land belonged to a group of fishermen. Actually, Veli Tumba is a very sleepy, peaceful village of fishermen. So Dr. Vikram Sarabhai approached the Archbishop, Bishop Pereira in Trivandrum, and he convinced him about the importance of starting a research in space activities. And Bishop Pereira called all those fishermen and told that, come on, this is a great event that is going to happen. It is going to benefit all of us. So better we will move away. They will give you better accommodation for you, and we can give this place for the space research. And all of them readily agreed, and the entire community was moved to another place, and they were rehabilitated there. And the first instant of space research happened in a church. That church building is still there, and it has converted into one of the best space museums in India, which is open to public. So this has been one of the, I would say, finest examples of, I would say, communal harmony. ISRO's beginning itself, it was in such great synergy, I would like to stress here. So, as I said earlier, the ISRO Satellite Center has been established. The Space Application Center at Ahmedabad was also established at that time, and they are concentrating on the payloads which need to fly in the satellites. And parallelly, as part of the launch vehicle development, Vikram Sarabhai Space Center was specializing in solid rockets. The need for liquid engines was also felt and understood at that time itself. And the Liquid Propulsion System Center was also initially formed in Trivandrum itself, in another place called Valiamala, some 20 kilometers from the city. And so basically, the infrastructure and the mechanism of expansion started in the period of 1970s. And when you talk about 1970s and the early 1980s, there was a two-pronged approach by ISRO, attempting to make our own launch vehicles, which has to be our strength, and at the same time make our own satellites. So in Bangalore, the designs were commenced, and as you know, the first remote sensing satellite, Aryabhata, was launched in 75, which was followed by Bhaskara 1 and Bhaskara 2. And our first communication satellite, Ariane Passenger Payload Experiment, that was made here and launched through the Ariane launch vehicle of ESA or CNES, as it was called at that time. We also started, after the success of Apple, we started making our own Indian communication satellites called INSAT series. And parallelly, after Bhaskara, we started making our own remote sensing satellites. Initially, all our communication satellites of INSAT series were launched from Ariane from the Kourou launch port of ESA, while all our remote sensing satellites initially were launched from Russian rockets. So this was because at that time we didn't have our own launch vehicle, and it was in the design phase. So that was till early 1980s. Parallelly, we were also involved in the design of launch vehicles, and after the sounding rocket experiments, in fact, the sounding rocket experiments are even now continuing. We have never stopped launching sounding rockets from Tumba, And every week on the Wednesday, there will be a launch, basically to study the upper atmosphere phenomena, etc. So that is continuing. The first launch vehicle in the full concept, SLV, satellite launch vehicle, with all solid 4-stage vehicle, it had a capacity for 40 kg payload. A satellite weighing 40 kg only was launched successfully in 1979, and you know, none other than our honorable former president APJ Abdul Kalam. He was the first mission director and project director for that launch. This happened in 79-80, and subsequently we augmented to the next generation what we call the ASLV, augmented satellite launch vehicle. You can see the difference is this is SLV, this is also SLV only, but it is augmented with what we call 2 strap-ons. So basically ASLV was conceived to demonstrate many of the technologies which was essential for our next generation of launch vehicles, which are much bigger launch vehicles. Like, for example, the concept of closed loop guidance, and also the concept of having strap-on rockets, and the concept of having different separation mechanisms, etc. So many technologies were built into this ASLV for demonstration. Of course, the first 2 missions were failures, but the next 2 missions were 100% success. We learned quite a lot from those failures. From there, this ASLV was capable of sending a 150 kg satellite in a low Earth orbit of 400 kg to 500 kg. But we took a quantum jump into the next generation of launch vehicle that is called PSLV, Polar Satellite Launch Vehicle, which was primarily at that time designed for sending remote sensing satellites. But this is a wonderful launch vehicle, beautiful launch vehicle, which is so versatile. We can send navigation satellites, we can send communication satellites, all sorts of satellites. And this is the launch vehicle which sent Chandrayaan-1. This is the launch vehicle which sent MOM also. So that is the beauty of this launch vehicle. It is still the workhorse of Isro. And almost 54 successful launches have been completed already. This has got a very high reliability based by demonstration, and there is a huge demand from other countries for sending their satellites to this launch vehicle. Very recently, we have given it for industry to make, and a collaboration or a group of industries led by HAL and L&T, they have taken up, and they are now in future PSLV will be productionized end-to-end by industry. So this is the story of PSLV. I'll come back later, and basically next gen launch vehicle is what we call geostationary satellite launch vehicle. So here, as I said earlier, PSLV was primarily for remote sensing satellite, but it can send communication satellites also, but the mass will be limited to around 1,200 kg. But as far as communication, our own communication satellites are required, the need was that we should at least have 2-ton capability, which can be expandable to at least 4-ton. This is the basic need, because number of transponders, the need from the country with respect to the communication channels requirement, huge number of transponders were required, which we are unable to match by if you are sending smaller satellites. So we need at least 2-ton capability. So in order to get that capability, one essential component what is needed is the technology of cryogenic propulsion. So initially we wanted to get the technology from Russians, but unfortunately due to geopolitical scenario, Russians finally did not give the technology, but instead of that, they gave 7 stages as such, as black boxes, so that we can use the stages to launch our satellites. And the initial few GSLVs were configured with the Russian cryostage in position, and from 2000 onwards, we had launched GSLV, which has got a capability of sending almost 2 to 2.2 ton capability of communication satellites into geostationary orbit. You should understand that when I say 2.2 tons, geostationary orbit is 36,500 kilometers, not 500 or 600 kilometers. So you know why 36,500 kilometers? Well, it was beautifully explained by sir in the morning, Seshagiri sir in the morning. He talked about our centripetal centrifuge equation. That gives the requirement for a geostationary orbit, because you need to have the rotational velocity of the satellite should be equivalent to the rotational velocity of the Earth, so that at any point from the Earth you will get you can see the satellite. The basic principle of communication, it should be visible. So if from one point if the satellite is visible, and if another point also the same satellite is visible, you can send the communication to the satellite, and satellite will communicate to the other place. It is as simple as that. But to reach that, we need to send the satellite at 36,500 kilometers. So reach that 36,500 kilometers with a 2-ton mass, we need a particular velocity at the time of ejection of the satellite. So to reach that velocity, you need more thrust. And that thrust is provided by the cryostage. So that is why cryostage is essential for meeting such kind of requirements. So as I said earlier, the evolution, if you put it in a nutshell, you have the initiation phase where we started based on the vision, the scientific quest started, we learned quite a lot, and we started building our capacity building, and parallelly international cooperation also was going on. And in the 80s, the experimental phase, as I explained to you, we had experimental satellites, we had experimental launch vehicles, which culminated finally into the PSLV, GSLV kind of operational launch vehicles and satellites. And expansion phase, we are further going to it. I will explain to that. Basically now, we have from GSLV Mark II, we have now come to GSLV Mark III, which is the most powerful launch vehicle that we are having, which has got a capability of 4-ton to geostationary orbit. And that is a launch vehicle which we are going for a Gaganyan also, because in Gaganyan, we need to send a payload which is of the almost 6 to 6.5 ton capability, but it need to go only up to 500 kilometers. So GSLV Mark III is quite capable of doing that. So that launch vehicle is our workhorse now. And apart from that, now we are on the design board for still powerful heavy lift, what we call heavy lift launch vehicle, which should be, we are aiming for at least 16 ton to 20 ton, which can be scaled up to even 50 tons, because that is also essential when we are talking about our future road plan for beyond Gaganyan, which I will come to that. So what we need to do after Gaganyan, we need to have our own space stations, etc. But ultimately, our limiting factor is a launch vehicle, so we need bigger launch vehicles. So we are also into that program in future. And at the same time, we are also developing new technology satellites, like high throughput satellites, hyperspectral imaging satellites. So we have to keep on par with the international and national requirement, and because the competition also so high in this present scenario, so we should live up to that. We are now also planning quantum communication satellites, especially with respect to the cyber security related issues that is coming up in a larger way. So the future is very, very exciting as far as either launch vehicle or satellite or other applications are concerned. So some of the major milestones what we have achieved till now, if you really ask me, as I said, 1963 has been the first sounding rocket. 1975 we sent Aryabhatta. 1981 was the SLV-3. 1982 first series of INSAT-A. And 1988 the first operational remote sensing satellite we launched. So these are all major milestones, I would say. And continuing with that, the 1999 in PSLV-C2, it was the first multi-satellite launch where multiple satellites including OceanSat as well as 2 satellites from abroad. This is the first, I would say, the commercial kind of mission that we have undertaken. We started in 1999, KitSat from Korea and TUPSat from Germany as payloads. We successfully launched at that time. And in 2001 was the first GSLV D1 with the Russian cryostage. First time we succeeded in sending this GSLV D1, and the beauty of this mission was that it was also the payload was EduSat, and you know the importance of EduSat. This is the first time we demonstrated and executed tele-education. I'll come to that part later. And 2008 also is extremely noteworthy, because in C11 we launched Chandrayaan-1 mission. This was a very, very exciting mission. And I also would like to add here that the excitement that we had, because it was not only a mission to the moon's orbit, we also landed one small unit into moon, which is called Moon Impact Probe, and that is still there in moon. So that was an idea germinated by none other than Abdul Kalam sir. And very quick time, within I would say 6 months, we made that Moon Impact Probe, and the images of the Moon Impact Probe taking the moon's surface before hitting the moon is still very popular. So that is then of course 2013 is our is another epoch-making launch, I would say. Our first satellite of our constellation of Navik, as Madam was telling, Nandini was telling about Navik. It was the Navik name was it was christened by none other than our Honorable Prime Minister only. So this Navik, I will come to that Navik later. This Navik first mission was done in 2013, and of course, this is Nandini's baby, I would say. 2018, MOM was launched. It was such a memorable launch for all of us. And here I would like to, again, in between, actually I forgot to add SRE also. Thank you, Nandini, for putting that, because I think that was a wonderful mission. SRE was never given its due, I would always say, because that is the first time, I think, we are all talking about MOM, where we entered into Mars mission for the first time. We are the first country to do it first time, successfully. So that is a great achievement. But SRE was also like that. SRE was also first time when we send a satellite to orbit and bring it back safely and capture it for the first time successfully. That also we only did. So that is the beauty of SRE. I would like to say that. And SRE, we could very, very successfully demonstrate, as she told, the re-entry part, wherein the kind of thermal insulation that we have given, no, that what you call the kind of tiles and other material of which you use for insulation, that was proved absolutely, and whatever we predicted, the temperature profile was also exactly same, and that gave us a lot of confidence for our Gaganyan program. I'll come to that. And this 2014, this is an epoch-making mission, that is GSLV D5, we launched with the indigenous cryostage. I think if you ask me as a scientist, I think this has been the biggest achievement by Isro. Why I am telling is, as I told you, we never got the cryogenic propulsion technology from Russians. So we started making our own from scratch, this design, which we could successfully demonstrate in GSLV D5. I think acquiring this cryogenic technology has been a game changer as far as Isro is concerned, which will not be known much to public. Everybody is, I would say, accelerated with the success of MOM, Chandrayaan-1, etc., etc., and rightly so. But I would say this is one step better, because acquiring cryogenic technology is something, it's such a complex technology, and no spacefaring nation will acknowledge you as a space power unless you have your own cryogenic technology. And that we could do successfully, and now we are continuing. Is because of GSLV D5, and I am extremely thankful to God that I was a real part of this mission. I was a vehicle director for this mission, and I know the kind of agony followed by ecstasy during this mission. Sir knows much better than me. He knows how we have struggled to make this success. So that is unforgettable part of our life. Similarly, these two things, 2017-16, it also did not get much attention in the public, but this was a very significant achievement as far as in the scientific world is concerned, is the demonstration of the reusable launch vehicle technology. You know, reusable launch vehicle, what we are contemplating is something like, it is a winged body, like an aircraft, which will horizontally lift off go to orbit and come back and land. That is ultimate that we want. So first time we, in a scaled model, this launch vehicle or this RLV model, the winged model was put on a solid motor. It was sent, and then it came back and landed in sea. So we could demonstrate the aerodynamic part of the winged model successfully. So this was a milestone achievement. And now with a full-scale model, in a short time, maybe within 1 year, we will be having the next experiment on this RLV. So we are in this path. We are not following what others are doing. We are trying in our own way to achieve this reusable launch vehicle technology, because the advantage, you know, is cost. All other launch vehicles, you know, they are called expendable launch vehicles, because each stage will be separated and they will fall into sea, and that's all. So only ultimately the satellite will be launched, and if it is coming back, it will come back. But launch vehicle as such is lost. So here, when you say RLV, the same thing is going and coming back multiple times. That is what SpaceX is also doing, but they are doing in their own way. Our design is slightly different, but which many others have tried but not succeeded. We are still trying that. And this, of course, this is a very important event wherein, for the first time, 104 satellites were separated in one go, which was a world record till last year. So this was a very exciting and challenging mission. And out of this 104, 88 satellites were from NASA, not NASA, from US. So the popularity and the confidence that the world has on PSLV was once again demonstrated with this launch vehicle. And definitely, as I said, Mark 3, first developmental flight was a huge booster for us, because the capability and the reliability of GSLV Mark 3 was established with this mission. And actually in the design phase itself, we had foreseen that GSLV Mark 3 will be the launch vehicle for our Gaganyan program. So all the basic requirements, margins, which are needed for a human flight requirements, which we call human rating, was already incorporated into this launch vehicle. So once we demonstrated the success or the functioning of this launch vehicle, it was much easier for us to human rate this launch vehicle for Gaganyan program. So some other major milestones, I would say 2018, this is our heaviest communication satellite, 5-ton, GSAT-11, was successfully launched. 2019, Chandrayaan-2, and if I remember correctly, apart from that, we also had the launch of the first high-throughput satellite, as well as the hyperspectral imaging satellite, HISE. So these were milestones in that year. 2019, of course, you know, Chandrayaan-2, the orbiter is still beautifully working. There are 8 payloads, and all the 8 payloads are giving wonderful images, wonderful data. The entire science community in the world are taking this data and making papers. I don't know what are all these startling discoveries that is in store for us as far as this mission is concerned. Of course, we wanted to land. We did not succeed. So Chandrayaan-3 will be done probably next year, middle or end of next year, wherein that mission is exclusively for landing in moon. So that is also going on. And this 2021 also was an epoch-making launch, because it's the first time a dedicated launch by our PSU, Public Sector Unit. We had formed a Public Sector Unit based on the new policy and the new reforms that the government has introduced in the space sector, where they wanted to enable our Indian private sectors to carry out their space activities also. Earlier, we didn't have a mechanism wherein those players can do any space activity. So now we have made that mechanism. There is an institution called InSpace was formed in order to regulate, handhold, as well as enable our private industries to academia, not only private industries, academia and other agencies, startups, to invest and make their own space activities. It can be launch vehicle, it can be satellite, it can be applications, it can be ground station related activities. So as a part of that, this was the first mission where the PSU contracted the Amazonia and the 18 co-passenger satellites as a purely commercial mission So this was also a game changer, and it will be a game changer for future launches. So here I just wanted to just dwell very quickly, because I think both Seshagiri sir and Nandini have very in detailed way they have talked about this, but still I would like to inform you that the applications in Earth observation is mind-boggling. And let me tell you that very silently, very effectively, the data from Earth observation satellites are being disseminated throughout the country to all the government departments, state government departments, and most of the state government departments are also making their own applications so that it reaches the common man as far as the various facets of activities are concerned, including resources, including agriculture, including crop formation, crop cycling, the drought-related information, where is watershed lands available. All these are continuously happening in a very continuous and I would say rather silent way. In fact, in 2017, Honorable Prime Minister had a detailed 3-day meeting in Vigyan Bhavan in Delhi, wherein he called around 167 government and state government departments, and he asked them to present what they have done with the data that was given by Isro with respect to remote sensing. And that was a very, I would say, very, very effective kind of meeting, where, based on which around 151 projects were once again formed. And I'm very happy to say that as on today, almost all those programs have been successfully completed. So this is a kind of activity that is going on with respect to remote sensing data. One particular example that I would like to tell you is with regard to the potential fishing zones. See, this particular thing has totally changed the lifestyle of our fishermen. Especially I would like to mention those fisher folks in Tamil Nadu coast as well as Gujarat coast, wherein now, you know, because of this information from remote sensing added with the kind of navigation capabilities that we have, exactly we can pinpoint where the shoal of fish is available. They simply have to go there, collect the fish and come back. So it is a lot of money saved in fuel, in time, in their energy, the effort. And let me tell you, last I would say 7 to 8 years, the kind of the lifestyle of these people have changed drastically. So this is a kind of advantage that you get based on the applications with respect to remote sensing. And I also don't have to tell you about the disaster management part of it. Now cyclones don't matter to us that much as far as human lives are concerned. You know, 10, 15 years back, if a cyclone, especially in Andhra coast, if a cyclone happens, the kind of death toll you used to hear about is 7,000, 10,000, 15,000 kind of scenario. Now it is less than 5 kind of numbers only are coming, and that too because these people, many people may not hinder to the warning given to them, and they will not move away from that place. Mostly it is because of that. So that is a kind of advantage. We can exactly predict ahead of at least 1 to 2 hours before how the cyclone, if the direction is going to change. That details also can be given. So that is a kind of advantage that you are really getting with respect to this kind of data. And of course, communication, I don't want to talk much because, as I said earlier, starting with your mobile phones, it's part of your body now. It is not a separate equipment, it is an appendage to your body. So starting with that and the kind of other applications that is going on, like, you know, the banking, the money transaction that is going on is mind-boggling. Nowhere in the world this kind of money exchange can happen. Let me tell you, whatever UPI applications that you people are doing, even in a petty shop, you can go and show your mobile and get the money transaction. So this kind of technology lapping up happens only in India, nowhere else. If you go to Europe, recently I was in Paris, this kind of transactions is impossible there. You cannot, still they are not reached to that stage, and if you want to find an ATM, you have to walk kilometers. You just see the scenario. Even in Puttaparthi, I can see just like that 3-4 ATMs here and there. So that is a kind of scenario. So the communication has revolutionized. Indians have a tendency to lap up all these kind of technological applications. So that is in one way good, maybe in one way not that good, but anyway, I'm not going to that part now. So that is broadcasting, teleports, cable. You mention it. Communication is mind-boggling kind of. And coming to navigation, as I said earlier, Nandini had very nicely elaborated the navigation constellation. Of course, ours is a regional constellation. Another definitely 3-4 more satellites will be going in, and maybe in another 2 years time frame. We are putting on that. The beauty is, let me tell you that at least 5 mobile phone companies have implemented Navic into their solutions. The chipset has also been put, and they are available in the mobile phones. So that update I wanted to give you, and it is slowly percolating into the different types of mobile phones. And one important thing is that in future, mostly government may give a regulation. I mean, they will bring a regulation in such a way that new mobile phones have to be with Navic solution also. So you just imagine the advantage. Suppose for some reason GPS is switched off, then the present way we are operating navigation, India will come to a standstill. So we don't have to bother. We have Navic, and the performance is, I would say, shade better than GPS as far as regional navigation constellation is concerned. So, so the only point is people need to have that conviction that whatever we make are also equally world standard. That conviction has to be there. Isro is also trying his level best to do its outreach programs so that this message is getting conveyed to the public, because public should be convinced, otherwise this will not happen. So I think slowly things are improving, and this will become a great boon to the Indian society in future. I am very sure, along with Gagan. Now I am very happy to say that the government has made Gagan mandate, the Gagan receivers mandatory in aircrafts. So this is a very epoch-making decision. Of course, it will take some time to implement, because aircrafts have a reluctance to change what is already there in their system. But once this is done, we are absolutely, this is one area where we will be absolutely Atmanirbhar, I would say. And of course, as I said earlier, we have to pursue space science related missions also, because we have to take care of our next gen, and their curiosity has to be supported, and we need to give them opportunities to build on their curiosity. So such missions are very essential for us. So I am not going into detail. Chandrayaan-1 I already told. Mom, definitely no more. I don't need to talk further, but she missed certain very exciting moments. I don't want to tell it now, but in some other time frame, I think she herself will tell some of the other nerve-wracking scenarios that we had as far as Mom is concerned. And of course, this is also, I am extremely proud of to mention about AstroSat. This is our first and only observatory in space. This also is a very great achievement, because this is the only satellite which gives a multispectral capability with respect to imaging. This is our, shall we say, our telescope in the orbit, and some epoch-making discoveries have been made by AstroSat, and this is a very popular satellite whose data is being used to the entire world now. And very recently we celebrated its anniversary in headquarters. And let me also add here that as far as Mom is concerned, she was telling we aim for 6 months, but it has served 8 years, and 3-4 days ago only we finally declared the end of life for Mom. Rather sadly, but it was from 6 months to 8 years was the success of Mom. Yeah. So that is, then Chandrayaan-2 I already told the scenario. SRE, anyway, I am not further dwelling into this because Nandini has more than adequate she has described SRE. One more interesting thing is she told the telemetry was blacked out at the last minute, we could not identify. One more interesting thing happened. Normally there is a die which will once it lands, once it floats, there will be a colored dye which will go around the, it will be spread around the spacecraft and which will be available, visible for 1 to 2 hours. Unfortunately, that also did not work. So, so that is why they found it very difficult to locate this. If had it been there, it would have been easily located. So that is an interesting story of SRE. So this is what I would like to add here, because I always say, she mentioned it, the beauty of a space mission and also the challenge of a space mission is because of 3 elements I will always say. One is known knowns, that is we know what we know very well, so we are dealing with that. There are known unknowns. We know very well what we do not know. So for that we take care, there are ways of taking care of that. But the most difficult part is unknown unknowns. We do not know what we do not know. So what do we do for that? That's what she was telling. As far as satellite is concerned, there is one advantage, we have time. If something unknown happens, still we have time to take some, as he said, on-the-fly corrections. It is possible in a satellite, but that is simply not possible in a launch vehicle. We don't have time. So unknown unknowns are always a threat to us, a challenge to us, both ways. So the only way is to see that, as he said, review, test continuously. ISRO's strength is testing. And by testing different ways of scenario, at least whatever is perceivable, some new things will come out, which we can correct. Second thing is inbuilt reliability. You have to have reliable systems, one order, especially when you talk about Gaganyan, it's one order better reliability has to be established. So that is the second way. We built enough redundancy, test, that's the only way. And then pray God, Sai Ram, that's all. That only is going to help us as far as unknowns are concerned. There is no other go. So this is a beauty and this is a challenge. That's what I would like to tell you. Then subsequently, this was another precursor to our Gaganyan, wherein we called it a screw module re-entry experiment, wherein the SRE was as he said, it was in 2007. The module was a smaller module, which is not as big, or the dimensions, etc., were different from what you have conceived for Gaganyan. So this is exactly the crew module where our Gagannauts are supposed to go, and that crew module we sent as part of one of the experimental missions of GSLV Mark III. It went to a suborbital mission, and then it came back, and we demonstrated the re-entry part, including the deceleration part. As she was telling, you have to reduce the velocity, and there are a series of parachutes which will further reduce this velocity, but it's a very complex process. The parachute has to open, for that pyros have to be operated, and then parachute has to be fully deployed, and then velocity has to come down, the CG has to be maintained. There's so many complex scenarios there, and the second set of parachutes have to get deployed, so it's and they should not get entangled. So many aspects are there. This we could successfully demonstrate. The SRE was landed exactly where we wanted, and they were retrieved. This is also important because crew recovery is also a very important activity where a lot of agencies or interagency activities are involved. So this was a very successful experiment we conducted in 2014, right. Then this is another pre-Gaganyan test that we conducted. This is called crew escape system pad abort test. This is also very important because, as I said earlier, the reliability of a system has to be one order better when we have humans inside. They are the payload, and our duty is to see that they come back safely alive. So we need to have escape systems to save them in case of any disaster, impending disaster during the ascent phase or the descent phase or the orbital phase. All these phases we need to consider. So during ascent phase, we have something called a crew escape system. So any time in the ascent phase, it can be in the launch pad itself, or it can be during the initial ascent part of the mission, things can go wrong. So what it will does is, this particular test was a particular scenario where we have simulated a disaster event in the launch pad. So from the launch pad, the crew escape system will operate. It will take the crew module away to 2 kilometers away and splash safely in the sea before the disaster happens. So that is the criticality of it. Suppose one disaster, let me say, is a impending explosion of a solid motor. Then the challenge is, the explosion is coming, and the exploding waves also are traveling in a particular velocity. Our crew module should be faster than that velocity, and it should escape that kind of impact and go beyond that and land and sea. That is a challenge, and that will involve higher Gs, etc. That is why we need very trained people to be in the crew. So when normal Gaganyan missions, if everything is normal, the maximum G that will be experienced is only around 3.5 to 4 G. It is not normally, it is not a big deal. But in these cases, it may go up to 8G, 9G kind of scenario for a short duration of time, which only trained test pilots kind of people only will be able to withstand. So that is a criticality of this, but this test we could successfully complete in the first attempt itself. So based on all these things only, finally in 2018, Honorable Prime Minister announced officially the Gaganyan program, where he declared one daughter or a son of India will go from Indian soil to space and come back safely. That also he added. And he gave a very, very stiff challenge of 4 years. He wanted this to happen this year, the 75th Independence Day of India. We were trying our level best. It was a very difficult challenge. But unfortunately, because of COVID, everything went to disarray, and we lost almost 2 years. But we are back on track now, and very soon we'll have the first unmanned mission. I'll come to that. So this didn't happen on a single day. The Gaganyan program, the human space flight program, the thought process has started as early as 2002, where initially a study team was formed, who had to debate and find out what is the kind of strategy we should take, what is the kind of technology that we should use, and what is the kind of orbit that we should go, how many people we should go. That initial studies were carried out from 2002 onwards, which was followed, the committees, that report was studied, and another committee was formed in 2007, again a study team, to further give more, I would say, flesh and blood to that program. And that culminated in 2011 into formation of a pre-project team of human space flight under Vikram Sarabhai Space Center. And they only carried out these experiments like pad abort test, the CARE mission, etc., what I told earlier. They carried out those experiments. And finally, we gave them government confidence that, yes, now time is mature to announce. And based on that confidence, it's not very easy to convince the government for such a mission. So then only Honorable Prime Minister announced this program. So this is the configuration of this Gaganyan. Basically, you know, this is a GSLV. Basically, it's a GSLV Mark III launch vehicle only, with these two solid strap-ons of S200 motor and the second liquid stage L110 with our C25 cryogenic stage. This is a powerful version of the earlier cryo stage propulsion which I was talking about in GSLV, and this is purely Desi. It's a 25-ton cryogenic propulsion stage, and on top of that is our orbital module with its crew escape system, what I was talking about earlier. So this is the overall configuration of the launch vehicle, and as on today, the launch vehicle is practically ready. Everything is completed, only fabrication is going on. There are certain other criticalities which I will just briefly tell you later. So if you talk about this configuration, this is the crew module wherein the crew is going to sit. This is designed for maximum of 3 crew, and initially we have designed the whole mission for 3 days. Subsequently, we will expand later once we get confidence with respect to the missions. And we have an orbital module, which is basically, I would say, the service, it intended to service the crew module. You know, this crew module needs, essentially the crew module needs a habitat for humans to survive. It needs oxygen, it needs hydrogen, it has to remove carbon dioxide, you have to maintain the temperature, you have to maintain the humidity. There are so many complex requirements within the crew module, for which we need different kind of mechanisms and systems, like you need a gas bottle, you need a pump, all those things are required. So for that, it will be housed in the service module with its own power generation. These are all the solar panels which is around, and also we need to control. Attitude control is required, so we need thrusters. So all these are put together in the service module, and the beauty is this service module will be there during the orbital phase. Once we start our re-entry, this service module will be separated, and only the crew module will start doing the re-entry. So that much things will be that much simpler. So this is the overall configuration, and on top of that, this is a crew escape system I was talking about, which consists of 5 different types of solid motors with high acceleration capability, which will take this crew module up and away in case of any impending disasters. So what are the prerequisites of Gaganyan? What we need? What is so special about it, if you ask? So basically, as I said earlier, we need human rating launch vehicle, which we have. Essentially, crew escape system should be there. And because of the overall, it's a new configuration which was not flown earlier, including the crew escape system. The overall aerodynamic configuration is new. We need to validate it using various tests, including wind tunnel test. Then launch pad also we need to modify, because since crew is there, safety is paramount. In case something happens in the crew, this pad itself, there should be mechanisms to safely take away the crew. So there are features which have to be incorporated. Then this is something very important, integrated vehicle health management system. We need to monitor the various parameters of the vehicle in order to detect an impending disaster. So that is the challenge. So any disaster, it can be a breach in the pressure cabin, it can be an impending explosion in the solid motor, or it can be an explosion in the liquid stage. It can be anything. But the important thing is we need to detect prior to the event happening. So it's a very complex algorithms are required, and very precise monitorings and sensors are required. So this is a new, altogether new thing which we are developing now. Then redundancy, as I told, reliability has to be improved. Normal launch vehicles, we have redundant systems only. So here we are talking about quad redundant. There are 4 systems running in parallel, so that even if one fails, systems are still stable and reliably working. And as I said, safety margins have to be more. So these are all prerequisites for such an important and such a critical flight. And as I talked to you about the human habitat, essentially what is required is you need a pressurized crew cabin with a doubled wall structure in order to improve the reliability. Even if one wall breaches, still the other wall will be able to take care of. When I say breach, it is basically because of the issue of space debris only. Small particles will come with a very high velocity. You would have seen the pictures what she has shown, no? Where for example, in Hubble telescope and all she showed. Such things should not create a breach in the crew module. Then, as I said, environmental control and life support systems, very essential. These are absolutely new to us. So we have made a very conscious decision, because nobody is going to give us the technology. We have tried. So we have decided that we will be designing from scratch. And we are doing that. We are almost successful now. This only takes some time to get demonstrated. Viewport is very important, because it's a contradicting requirements that it should be transparent, we should be able to see, and at the same time the interfaces should be that it should not lead to a leak. So this is very complex. Then we have also consciously decided that we are a very responsible entity, so we are going for green propulsion systems, so that the kind of pollution, etc. don't happen. Then, as I said, parachute systems are very complex. Avionic packages, this I have already told, meteoroid and orbital debris shield we require to protect. Then very new thing is human-centric products. We have to make the humans comfortable in the new habitat. We need to have for example, we need to have diapers. That kind of requirements are, then food. I will talk about food also. So these are all absolutely new to us, which we are doing now. Then, of course, display console, and what are all the controls that humans need to carry out if required. So all these things are being developed. And just to briefly tell you about its ECLSS, that is Environmental Control and Life Support Systems. You need air revitalization system because carbon dioxide has to be removed, odor has to be removed. These are all you don't feel in Earth, but here in a enclosed environment in the space, these are all very, very critical things. The odor and trace, then cabin pressure has to be controlled. You have partial pressure of oxygen has to be maintained. Heat and humidity has to be removed because always human heat will create perspiration and that will create humidity. And the entire thing has to function in a closed loop system. So that's what I was telling earlier. These pumps, gas bottles will be part of the service module. And the mission profile is simple. From shower it will lift off. And if everything is okay at a particular altitude, the crew escape system also will be separate. And only the crew module and service module will be there with the cryo stage. And an appropriate altitude, the cryo stage will separate the crew module and the orbital module as such. And for a maximum of 3 days. As sir was telling, 1 day 16 orbits. So 16 into 3, 48 orbits maximum is possible. And then we'll start re-entry. We'll reorient in such a way that the service module is escaping. 90-degree reorientation is required because once service module separates, otherwise it will go and hit the crew module again after separation. That should not happen. So we have to reorient and then again reorient so that the entry, as he was telling, the nose should face the heat first. So that will be done. It will re-enter, then parachutes will deploy in a sequence and it will splash down in sea only. Our design is to splash down in sea and not in land. So the optimal point what we have decided is very near Andaman Nicobar Islands in the Arabian Sea. But if required, we can land in the Bay of Bengal, or if required, we can do it in the Arabian Sea also. So this is the overall mission planning. And precursor to that, a series of missions we are going to. We have very clearly our strategized in such a way that reliability is paramount. We cannot make any compromise, even if it takes time. So before we attempt for the first manned mission, we have to be 100% or 200% sure that all things are okay. So we need a series of demonstrative tests. As I said, design, everything is okay. Our strength is testing. So we have planned a series of airdrop tests. We call integrated airdrop tests. Around 17 tests are planned starting from December this year, wherein the crew module will be taken by a Chinook helicopter 5 kilometers away, and then it will be dropped. The parachutes will deploy, and we will demonstrate the deceleration part of it, the splashdown, and the entire gamut of other stakeholders, including Indian Navy, will be around us to start practicing and rehearsing the crew recovery procedures. So this is a very elaborative kind of test we are planning for the next whole year. Apart from that, we have configured a test vehicle, launch vehicle itself, wherein 4 such missions we are planning, wherein this launch vehicle will take care of this crew module, and we are going to simulate various failure modes of the crew escape system requirement at various altitudes of the ascent phase, so that we can demonstrate that in such events, the crew module will take the crew escape system will take the crew module away and land safely. One example, what I told is pad abort test. Apart from that, at different altitudes, maybe 10 kilometers, 20 kilometers, we will be releasing the crew module with the crew escape system and demonstrating this. So 4 tests are planned. Apart from that, 1 more pad abort test is planned. After a series of these tests are over, we are planning 2 unmanned flights, exactly like the manned flight without the man in picture. And the 2 unmanned flights, if it completes successfully without any blemish only, we will be attempting for the manned mission. As on today, the first unmanned mission we are planning by end of next year, 2023. And if everything goes well, we can see the first manned mission either by 2024 end or 2025 beginning. This is our present plan. So I will wrap up quickly because we are running out of time. We are, as I said earlier, this is not an Isro mission. This is a pan-India mission. We are only, I would say, triggering or catalyst for this entire mission. It is a totally synergetic way of collaboration with the entire stakeholders. I'll just give a glimpse of these stakeholders. We have BARC, we have Indian industries. More than 80% of our sub-assemblies and structures, etc., are being fabricated by the Indian industries only. We have academic institutions for various experiments as well as some of the algorithm developments. We are reaching out to academic institutions. Actually, we have also floated a expression of interest for various experiments to be done in the orbit. So one series is already over, 5 experiments have been already chosen with the academia, which will be planned for this unmanned mission. I was talking to Vice Chancellor also earlier yesterday, wherein please get into this mode. We can have discussions. If you have good experiments, we can still try. We have one more unmanned mission, maybe one more, and we have manned mission. Lot of opportunities are there. So we need to have some interactions on this particular aspect. And then DRDO, all the defense labs are part of us for various activities. CSIR, Indian Army, Indian Navy, and of course Indian Air Force. All are part of us for various, I am not going to details, these are all involved. Similarly, it is not only Indian, we have international collaborations also. Actually, the astronauts, initial training of the astronauts were carried out in Russia, and they have come back. That is why we are told Glab Cosmos is helping us on this. And also the crew seat and the crew suit are provided by Russia. For initial flights, we will be using that because it's already proved. Many missions, hundreds of missions they have carried out. No point in reinventing the wheel at that time. But at the same time, we are developing our own crew suit, and that's going on. But till then, initial missions, we are going ahead with this. Then we have ground station support from Australian Space Agency, ESA, NASA, our Amazon Web Services. We are everywhere because this is one mission where we want visibility 100%. During the entire ascent phase, as well as orbital phase, as well as descent phase, we want 100% visibility. So we cannot depend on our own earth stations, we need other support. So that is why, and very good support we are getting from the international community on this. Because as far as human spaceflight is concerned, there are no politics involved. Everybody is on par. Maybe some money is involved, of course. That is part of it. So that's the international collaboration I was talking about. And crew recovery, I already told, it's a very complex aspect. We have to locate them, and we should be ready to grab them. So we should the landing point should be very accurate. And in case of any mishap, we should have enough resources to see that at least within 1 or 2 hours we reach where they land. So in case of unexpected events happening also, we should be ready to save them because they can land anywhere in the sea. So international cooperation also is there. There is an agency, a private agency who is adept in this. Then our Coast Guard is doing a very good job. They have a lot of international cooperation. So it will be a totally international effort, I would say, as far as crew recovery is concerned. And I told you that the initial phase, 1.5 years of training, specific training, our astronauts got trained in Russia. Actually, our astronauts have been selected. There are 4 astronauts, and they are successfully completed the Russian leg of training. And I'm very happy to say that there was very good appreciation by Russia on their performance. They said they are even better than many of their own cosmonauts. So, and now they are undergoing their own, our own Indian specific training. We have a huge astronaut training facility which we have built in Bangalore itself, and they are undergoing our missions, our specific training. And that also, let me say, it is very new to us. We never knew what to do from the beginning. So we have started from scratch. We learned a lot of information from Russians, and we also have discussed among ourselves. And as far as the health of astronauts are concerned, it's absolutely a new area wherein our Indian IAM, Air Force Medical Group, they are taking care of this entire matter because they are adept as far as jet fighters are concerned, jet pilots are concerned. So this is also a very involved process, and we are into that job now. And for that, a series of simulators are also required because we need to simulate the flight conditions, we need to have the display, we need to have mock-up wherein astronauts will sit and they get a feel of how the flight is going on. So these are, it's not simple things, very complex things, but we have made a few of them, some more are being on the pipeline. So all these things also take some time also. So all these things are going, so many activities are going in parallel in a hectic way. We have lost 2 years, we want to make up for that time. And this I want to spend one time, because government has one slide. Government has announced space sector reforms, as I told earlier, in order to make industries, academia, and other startups to carry out their own space activities. So based on that, in space, a mechanism has been formed, which acts as an enabler, an authorizer, as well as a supervisor. Also, we have presented to the cabinet a space law, which has to form to a bill, as well as a space policy. Both are with the government. Some discussions are going on, and I hope very soon this bill will be enacted, so that things will be very clear as far as the private players are concerned for the space-related activities. And I also tell that this in space is a mechanism where academic people can also approach. As Sir was telling, no, we have initial discussions with respect to technical feasibility. Then you can apply to InSpace, and they will see that your requirement, for example, making a satellite, is fulfilled. So they are the agencies to do this now. You have a mechanism now. And before concluding, somebody asked me, what are the spin-offs? Do you have any spin-offs with respect to the space activities? Let me tell you, I just noted down a few for those who are interested. Due to space missions, I don't know, huge number of spin-offs have been given to the society. One classic example in the Indian context, let me tell you, when Rakesh Sharma went to space, regarding the space food, CFTRA developed some formation of frozen food. And that is nothing but what is coming out as MTR now. It's very famous now. MTR foods, you get biryani, you get pulav, everything was developed for Rakesh Sharma in 1984. So this is a classic example how it is, how this, the spin-off of space activities. I think vascular bypass for removing blocked artery, I think some of the key techniques are evolved from space technology only. Then there is a infrared ear thermometer, which is very frequently used now. This is a non-pervasive way of measuring the ear temperature. Then ventricular assist device, which is much smaller in size. Then ophthalmologists, they use this technology for tracking eye movements. This was basically evolved out of the experiments they conducted for docking. So this is one classic example. Cochlear implants. Some of these technologies are used. Artificial limbs, the actuation elements used in space, for example, for docking, etc., they are using for artificial limbs. LED for treating tumors, that's a new thing. Like that, I can go on. I've just told a few. There are hundreds of offshoots that is coming in due to the activities we carry out in space research in orbit, in low or near zero gravity conditions. So let me conclude with the last slide. This is, I'm quoting Honorable Abdul Kalam ji, look at the sky, we are not alone. The whole universe is friendly to us and conspires only to give the best to those who dream and work. Here I just would like to tell you, young guys, I would like to reiterate, I will like to add on to this. Yes, continue to dream, but don't sleep. Thank you very much.
I request the entire house to join me again in giving a loud round of applause to Dr. Umamaheswaran. From the west coast of India, Tumba Equatorial Rocket Launching Station, to the east coast of India, Sriharikota High Altitude Range. From the launching of sounding rockets that are used to study the Earth's ionosphere, to the launches of geosynchronous launch vehicles, geosynchronous satellite launch vehicles that can launch satellites into the geosynchronous orbit. From launching sodium vapor payloads to study the ionospheric equatorial electrojet, to sending satellites to Moon and Mars, and holding the record of launching the highest number of satellites successfully with a single launch vehicle. The story from INCOSPAR to Isro has been stellar, outstanding, phenomenal, and inspiring. Capturing this stellar journey of over 50 years or 5 decades into a talk of 50 minutes is a mammoth task. And sir, you have really given us a glimpse of every milestone that ISRO has achieved through these 5 decades in a wonderful and inspiring manner. We hope to see you again and again here, sir. Now I request the Honorable Chancellor, sir, to kindly join us on the stage. Now, I would like to request the revered Chancellor Sir and Vice Chancellor Sir to felicitate Dr. Umamaheswaran and give away a token of love and appreciation. At the very outset, I would like to thank the founder chancellor of our institute, Bhagwan Sri Sathya Sai Baba, for blessing us always with his immense grace and for blessing us with such eminent scientists here amidst us. I would like to request the house to join me in another round of applause for all the 3 speakers. I thank the institute administration, campus administration of all 4 campuses, all the research scholars and students for joining us here today. Before we conclude this session, I have a couple of announcements to make. The two distinguished speakers for the afternoon session, Mrs. Nandini Harinath and Dr. Umamaheswaran, will be interacting with the research scholars from both the campuses after this session. All the men research scholars are requested to stay back in the auditorium. The women research scholars can proceed to the Multimedia Learning Center. The students of 3rd BSc Physics and Department of Physics students from Prashanthi Nilayam campus are requested to be seated in the auditorium itself. Tomorrow, Dr. Seshagiri Rao would be interacting with all the physics and mathematics students and research scholars from Anantapur campus from 10:30 to 11:15 a.m. when you will be notified later. From 11:15 to 12 p.m., Sir would be interacting with the students and research scholars of physics, data science and mathematics departments from Brindavan, Muddinahalli and Prashanthi Nilayam campuses. From 12 to 1 p.m., Dr. Seshagiri Rao would be interacting with the faculty of Department of Physics and Mathematics and Computer Science of all 4 campuses. Venues will be notified later. We shall end the program with Om Shanti Shanti Shanti. Om Shanti Shanti Shanti. जय बोलो भगवान श्री सत्य साई बाबा जी की जय. Thank you. Saira.
यत्र पार्थो धनुर्धरा